My dear friends, welcome to Rajashekhar classes on Applied Data Science with Python. This is lecture number 509. In this lecture, we will try to understand feature engineering on graphs, JACCARD and COSINE similarities. We already learned about how to construct the data set. What we have right now is a data set like this. We have data set where we have source vertex, we have destination vertex, and the class label of you have class label. Of course, some of them are zeros and some of them are ones, isn't it? But what you have here is basically pairs of vertices u1 comma u3, u1 comma u6, u1 comma u4. Basically pairs of vertices. Now you can't perform machine learning on this. So what we will try to convert this into format, we will convert this into format like this, isn't it? Where you have your yi, here you have features f1, f2, f3, so on, fd, isn't it? There are d features and yi is label. Each of these features, so for example, feature 1 that we have here, let this feature 1 is a graph theoretical feature. I will explain some of these features in this video itself, but the core idea is, given these pairs of vertices, that is u1 u3, u1 u6, u1 u4, so on, isn't it? This feature 1 basically takes pair of vertices u1 u3. Think of this is like function and give a value. So what you are trying to convert is given pair of source and destination vertex, source vertex and destination vertex. We will come up with multiple featureizations in this section of the chapter. Of course, we will come up with sensible featureizations. These featureizations are graph theoretical or graph based. We will also learn some non-graph based also. So in a nutshell, I can say we are trying to convert this pair of vertices into some numerical or categorical features, isn't it? Numerical or categorical features or binary features. Once if I have this setup, I do this, isn't it? In my test, if I am given ui comma uj, I will again compute these featureizations f1, f2, f3, so on, fd. Whenever you are given graph based machine learning problem, featureization is the most important task. So this is called anyway. I will keep, there is the IPython notebook. What is that particular IPython notebook name? This is fb underscore featureization, fb underscore featureization dot ipynb. I will keep this particular IPython notebook in the description section, even in comment section of this particular video lecture. I request all of you to go through this particular IPython notebook where you have everything, isn't it? Where this is whole IPython notebook is just going to work how to featureize graph based data. Having said that, I have training data after EDA. At the end of the EDA actually created this file, isn't it? And I am loading it now. As you might remember, we have 1.78 million vertices or nodes or people who have 7.5 million edges between them with an average in degree 4.2399, average out degree 4.2399, isn't it? Let's look at the couple of very simple featureizations. The first one is called JACCARD distance, isn't it? Which one? First one is called JACCARD distance. Before we are going to JACCARD distance, let's understand very simple terminology. Imagine if I am user U1, if I am following, if I have user U1 and I am following U2. Yes, I am following U2. Let's assume all these people. Let me assume U1, U3, U4 is following U1, U3, U4 are called followers, isn't it? They are following U2, isn't it? U1, U3 are called the followers of U2. These are called, which one is called? U1 is called follower and U2 is called followee. U3, U4 also called followers, isn't it? Yes, U1, because just see, U1, U3, U4 are called the followers of U2. These are called followers because U1 is following U2, U3, U4 also following U2. But the one who is being followed is called the followee. So in this relationship, U1 is called follower and U2 is called followee. Simple terminology. Now what we compute is something called JACCARD distance. Let me explain what JACCARD distance. Imagine I have two vertices U1, U2. Suppose U1 being followed by U3, U4, U5, isn't it? Now the same U3, let's assume, follows U2 also. Just assume I have a vertex U6 also. If I just from this particular graph data, what are the followers of U1, U3, U4, U5? What are the followers of U2? U3, U4, U6. Now I have two sets here. So the first one, the set of followers of U1 and second one is followers of U2. Let's call them as set capital X and set capital Y. So the given any two sets, JACCARD distance basically says JACCARD distance between between two sets is J equal to size of X intersection Y by size of X union Y. In a nutshell, what it's computing here is, look at these vertices U1, U2. Just see, look at these vertices U1, U2. There is a very high chance that U1 might be willing to follow U2 and similarly U2 might be willing to follow U1 because there is a lot of common followers. Just see, if you observe carefully, U3, U4, U3, U4, isn't it? There is because there are a lot of common followers, which means their intersection could be similar, or they could be their interest could be similar, isn't it? Which means their interest could be similar, or all could be belonging to a set of friends, because all of these reasons, if there is a lot of overlap between set X and set Y, so the intersection here is 2 and the 4 elements in the union. Therefore, what is the value? 2 by 4. So the JACCARD index is size of the intersection between two sets divided by size of the union between two sets. So the JACCARD distance between the sets of followers of U1 and U2 is 2 by 4. The larger the JACCARD index, the higher is the probability that there exists edge between these two vertices U1, U2. That's the logic we are applying. JACCARD index is not limited to only graph theoretic stuff. JACCARD index is used even in sets. Whenever you have two sets and you want to measure how similar these two sets are, JACCARD index is very simple metric, very simple idea. Again, I can compute JACCARD distance between followers, JACCARD distance between followee, isn't it? I can calculate JACCARD distance not only between followers, I can also calculate JACCARD distance between followee. If I have two users u1 and u2, I am taking the set of all followers of u1 and taking the set of all followers of u2. I am computing the set intersection by the set union, isn't it? Just the way I am doing for followers, I will do it for followee also. Very simple, isn't it? We are just going to implement each of these metrics. We will use all of these metrics or measures or features in the actual model later. So I am creating two features here. One is called JACCARD distance for followers and the other is called JACCARD distance for followers, also followees. So I have two measures here. These are sort of like similarity measure. Basically, I have two measures: JACCARD distance for followers, JACCARD distance between followees. So given any two pairs of vertices or two pairs of nodes, I can compute set of all followers and get JACCARD index. Similarly, followee of ui and uj and compute JACCARD index j. How it is working? This is basically taking two vertices ui and uj as inputs and returning a fraction for it, a fraction which lies between 0 and 1. And why did we pick this? Because logically we know that if two users or two vertices ui uj tends to have more overlap amongst their followers and followee, if they tend to have larger overlap between the followee set or follower set, then the chance of having an edge between them is high. So our first metric is called JACCARD distance. Again, JACCARD for followers and JACCARD for followees. We learned cosine distance between two vectors when we learned natural language processing. If I have two vertices, you can compute. If you have two vertices x and y, if you have two vertices, this is about JACCARD distance, is the size of x intersection by x union y. Now we will try to understand if you have two vectors x and y, you can compute the cosine distance or cosine similarity just like the two vectors. There is a modified form of cosine distance called Otsuka-Ochiai coefficient. Anyway, just try to search for this particular measure in Wikipedia. What is the difference between cosine distance and Otsuka-Ochiai coefficient? In the case of Otsuka-Ochiai coefficient, in denominator we will keep under root of number of elements of x into number of elements of y. This is basically a simple variation of cosine distance. This Otsuka-Ochiai coefficient is a variation of cosine distance which says instead of vectors I have sets. Imagine if I have set x and set y, I can define the size of the intersection by the square root of the number of elements in the number of elements in number of elements in x and number of elements in y divided by number of elements in x multiplied by number of elements in y, isn't it? This is just try to understand what is the difference between what is the difference here. In just it is similar, only you are keeping, in the case of Otsuka-Ochiai coefficient, just we are keeping under root for denominator, isn't it? Numerator is same. Yes, there is a Wikipedia article, just you can go through the Wikipedia article on it. The cosine similarity is basically this: if you have two vectors a and b, if you have two vectors a and b, this is your simple definition of cosine similarity. Now in the same article, you can see this one, Otsuka-Ochiai coefficient. Just see this one, what it says, just observe this one. This one is same thing. In denominator, I have under root of number of elements in A and number of elements in B. Otsuka-Ochai coefficient, which is used, A and B are sets. This is simple extension of cosine similarity. Two sets instead of vectors. So we are exactly using this as next important distance metric. Obviously, cosine distance will be high if there is a larger overlap between the set x and set y. Imagine if x and y, let me assume, if x and y are overlapping a lot, this is my x, this is my y, then you will notice that the numerator is large, the denominator is fixed. Let's assume number of elements in x is 20, number of elements in y is 30, number of elements in x intersection y is 18. So the cosine distance, cosine similarity is number of elements in x intersection y by number of elements x in by number of elements in x and into number of elements in y. So this cosine distance is larger when there is a large overlap. The primary difference is denominator compared to JACCARD. Instead of using the size of the union, we are using number of you are using number of elements in x multiplied by number of elements in y. Just I am comparing this particular measure with JACCARD, isn't it? Just try to recall JACCARD. In JACCARD, what we were saying in JACCARD measure, we are saying like this. Just if you recall JACCARD measure, this is cosine similarity, isn't it? What about my JACCARD measure? What it says? This is JACCARD measure. J equal to number of elements in x intersection y by number of elements in x union y, isn't it? This is about cosine similarity or cosine measure, isn't it? That is there is small difference, isn't it? This is a cosine. This one is this is cosine distance, isn't it? Cosine distance is larger when there is a larger overlap. The primary difference is denominator compared to JACCARD. Instead of using size of the union, here in JACCARD we are using size of the union. We are using number of elements in x into number of elements in y, isn't it? We still, just if you observe carefully, we still not reached the graph theoretical features. In my next lecture, that is in lecture number 510, I will start page rank. Just try to go through this lecture. If you have any difficulty, please keep a comment. Next lecture is certainly one of the best important concept for this particular case study. Thank you very much. Just I would like to show you that particular IPython notebook. Just see, this is my anyway, I will keep this particular IPython notebook in my comment section as well as in video description section. Just I kindly request all of you just go through this particular IPython notebook, social network, graph link prediction, Facebook challenge, isn't it? This is reading data, everything is there. JACCARD for followers, JACCARD for followees. Just we calculated cosine distance. Just see, this is cosine distance. Just go through this particular code. This is easy and simple and straightforward code. As I told you, I will keep this particular IPython notebook in description section as well as comment section of this particular video. Thank you very much.